Okay, today we're going to look at a special case of an inscribed angle. So the vertex is still going to stay on the circle. Hasn't moved yet. We'll get to the inside and outside later on. But it's an inscribed angle that meets a special condition. So we get something called a tangent. It looks like that. Okay. So my question is, that line is called the tangent line. What is it? Talk amongst your group then. Write a definition. You got a minute. Go. Remember, KISS method. Keep it simple, stupid. Don't overcomplicate it. Just answer the question.
A line on the outside of the circle.
Got it?
A line that's next to the outside of the circle but does not go in.
What do we got? We're still arguing? All right, I'll come back. It makes me awkward to watch you argue. Or makes it awkward. What do we got? Okay. Dennis, what do we got?
What if it's like, isn't that a chord though? It's like a chord does it. Chord. Like, can you say
Done arguing?
no?
Still arguing? I don't want to come over there. All right, I will. What are we arguing about? It does. That's what that one point means. But remember, it's a line, so it goes on forever. So can you answer your own question? How many points is that?
I think it's just a line that only intersects the circle at one point.
Okay, a couple things before we start looking. Whoa. Catch this, guys. Couple things to think about. Even though that circle in the picture is a solid green thing, that's not a circle. What's the circle part? Yeah, the edge, like a hula hoop. Okay, so when you talk about the outside of a circle, the outside of the circle would imply something way out here. Okay, this would be outside of the circle, this would be inside of the circle. You can either be on a circle, or you cannot be on a circle. There's no edge to a circle. Does that make sense? Okay, good. So, what do you got?
A line on the outside of a circle with only one point.
Okay, now based on what I just said, how would you change it?
A line with only one point
Keep it simple.
that, yeah,
Where is that point?
that doesn't go through.
You're overcomplicating. Help her.
A line that has only one point on the circle.
Boom. You just need the word on. You just have to get your preposition squared away. That's it. Okay. Number one, it's a line. So it has to go on forever. Will we see tangents that are segments and rays? Yes, but by definition, we're going to start with it being a tangent line. It intersects the circle in only one point. If I tilt that line and have it go through the inside part of the circle, it's going to extend and hit in two spots, which then generates a chord, which we don't want. We just want that. Okay, good. Intersects at exactly 1 point. What appears to be true in that picture? Other than the fact that it intersects at 1 point. Anything true about, let's say, angles? Senor? C, senor?
The radius seems supplementary to the angle.
I think you may have used the wrong word.
Yeah, perpendicular.
Perpendicular. Okay. Do you all agree?
Yes.
If I draw this radius in, does that appear to be perpendicular?
Yes.
Okay, and in fact it is. That point where the line hits the circle is called a point of tangency. And it does in fact make a right angle. How do we know that? Have we ever accepted the statement, well, it looks that way, as a justification? Go ahead. I lost you there in the end. Correct. But how do we know it's perpendicular? Or how do we know it's a 90-degree angle?
If you turn the radius into a diameter.
Hold on. If I turn the radius into a diameter. All right, I'm with you.
And then find the measure of that angle, and I need to half the circle.
How big is that arc? 180. Where's the vertex? On the circle. So it's still an inscribed angle, which seems a little weird because we're used to inscribed angles that look like this, where the two sides of the angle are chords. But now all of a sudden we've got this weird scenario with a tangent. It's still an inscribed angle, it's still on the circle, and therefore the angle measure is half the intercepted arc. It intercepts a semicircle, so therefore that puppy becomes a 90-degree angle. Okay, good. There's a couple, well, there's a new word up there, trichotomy. Does anybody know what that means? No? Trichotomy means three possibilities. You could have a dichotomy, two possibilities. The lights are on or off. You could have a trichotomy, and this is a trichotomy. You take a line, and you have it interact with a circle. It can only interact three possible ways. And this seems kind of obvious, maybe, for me. I don't know if it seems obvious for you, but it either doesn't hit the circle, it hits in 1 point, or it hits in 2 points. Remember, the center is not a point on the circle, therefore it can't hit in 3 points. A lot of people say, oh, if I just make that go through the center also, it's going to hit in 3 points. Doesn't work that way. Okay, so definitions were solid, we're good to go, let's move on. We did that already, we know that. In this particular picture, how long is AC? Now you might want to bust out your calculators, by the way. In fact, not might want to. Get out your calculators. Tell me how long AC is. Say again? Somebody back that up?
Yep.
Yep, good. How'd you do that, Ben?
You just use like the Pythagorean theorem, and you do 13 squared plus 2 squared, and then you do the square root of 5.
Good. Okay, that is a right triangle. Now, you're going to see scenarios as we progress through this where I'm going to tell you that that line AB is perpendicular, is tangent. I'm not going to give you the right angle, and you're going to have to remember that. All right, now let's make it a little bit more interesting. 14.3, is that what you said?
Yeah.
Outstanding. Quick comment though, don't get the two tangents confused. The tangent that we're talking about now is a line, like it says up there, it's a physical object. The tangent we've been dealing with before is a trig function. They're different things. Sometimes, however, will use trig and tangent trig function while working with a tangent line. It gets a little confusing. Why are they using the same term? I have no idea. That we know already. So this is a two-way street. If it's tangent, it's perpendicular. If it's perpendicular, it's tangent. Question?
Can you go back to the tangent?
That or this?
Oh, yeah, that.
That. All right. Simple question. Is FR tangent to circle O? Right off the bat, you're just going to fire off, well, you got a 50-50 chance, right?
Yeah.
Why do you say yes? Because it looks that way?
Because it's all smooth.
Yes. But you don't necessarily know what happens if I turn FR into a line, or you don't know what happens if you get very close. If FR is the tangent, what must be true? Angle R is 90 degrees. How do we know if R is 90 degrees? There's at least two ways, four ways off the top of my head that I can think of to check to see if angle R is 90 degrees. What do you got?
You should do like the log sine, or no, not log sine, but like sine and cosine of like inverse. You can find that in there.
Good. One way you could do it is to use trig. Now that's going to require a multi-step problem because I need to know one of these other angles. But I could find angle F by doing something like the tangent of F is equal to 5.5 over 13.6. Then get angle F, then do law of sines. There's a problem though. How long is OF, octopus ferret? How much? Why 19? No.
Oh, wait, no, you do.
5.5 plus 5.5.
9.5 plus 5.5, why?
Because it's 5.5 is the radius, and
Yeah.
then 9.5 is the...
OG, aside from being the original gangster, is also the radius of the circle. Therefore, we know that that is going to be 15? If I did my math right? Yeah. So F will, tangent of F will tell me the measurement of angle F, then I can use law of sines. However, if that is a right triangle, what else must be true? What works in all right triangles? Pythagorean theorem. Check that for me, please. See if it works.
Almost.
Almost.
14.67.
Ooh, so close. Would you say yes or no?
No.
No, because it's got to work exactly. Does 5.5 squared plus 13.6 squared exactly equal 15 squared?
No.
The answer is no. Then what do we know? It's not a right triangle, and therefore not tangent. Very good. Not a right angle. Which means that if I zoomed in really close, I'd probably have something like this. This line would come in and then maybe extend a little bit further and hit at another point if you zoom in real close. So it doesn't work. Questions? Beautiful. We've got these things called common tangents. They are lines that are tangent to two circles at the same time. They pop up every once in a while. We're not going to make a big deal of them, but there's two types, an external and an internal tangent. You ever play a game Shoot the Moon? You know what I'm talking about?
Isn't that the thing where you like move the like two bars and this like the ball?
Yeah, you got the big metal ball and then the two bars, and you slide the bars apart and you try to roll the ball uphill by dropping it and then getting
Oh, yeah.
Oh, yeah.
Yeah, I
I
remember
played
that.
that.
Yeah, I'm.
Yeah. In that scenario, you have a couple of external tangents. So the ball is the circle, and the rods that you're moving in and out represent the external tangents. That's kind of a 3D thing, but go back.
Yes.
Yeah. Good.
I'm sorry.
That's all right. We're doing okay for time. Take a point outside a circle, A. It will hit the circle at 2 points of tangency. In this case, E and R. E and R can never be endpoints of a diameter. Why?
Because the angle of B is not 180.
Correct. If B was 180, what would you know about the segments EA and RA? Well, never mind, it's a silly question. You couldn't even have them. They wouldn't share a common point. They'd be parallel. Okay, so this is a case. 2 points of tangency. And we get these segments, AE and AR. Those are called tangent segments. Not only are they called tangent segments, but what appears to be the relationship between AE and AR? Well, hold on. Yes, you got 90 degrees, but that segments, what about EA and RA? Yeah, they appear to be equal to each other. In fact, they are. Okay. And of course, appear doesn't work. How are you going to prove that? It's real simple. By the way, what kind of figure is bear? It is a kite. Everybody good with that?
Yes.
If you know that EA and RA are congruent, you know that BE and BR is congruent, that ends up being a kite, and you go from there. Okay. Now, how would you prove that? Well, I do know, let's pretend I didn't know that EA and RA are congruent. I can draw in the segment BA, which I know is congruent to itself, and I can prove the two triangles are congruent. And then once I know the triangles are congruent, I can go on. Okay. Regardless, they're equal to each other. This is what's called the walkabout problem. A, B, and C are all points outside the circle, and they generate a bunch of tangent segments. So in this picture, we have FB congruent to EB, I have CD congruent to CF, and I have AD congruent to AE. It's called the walkabout problem because you start at one point, you work your way around, or you walk around the figure to get all the other measures. So for instance, how long is CD? 9.5. How long is AE, aardvark elephant? 3. How do I find EB and FB?
Don't you add up all the points and then subtract it from 50?
Yep. I know the perimeter of that triangle is 50. If I call these X, these would be congruent to each other. 2X plus 3 plus 3 plus 9.5 plus 9.5 would equal 50. And we could take that and make it more complicated by maybe instead of a triangle, we've got a quadrilateral around it, or we've got an octagon around it. These type of walkabout problems pop up quite a bit. This one's a little trickier. We're going to end with this. If I want to know the circumference of circle D, what do I need to know? Radius. So find the radius of that circle. This is kind of working backwards from example number 1. just sit there, do something. Set up an equation, solve it. What kind of triangle is that, by the way? It's a right triangle.
Oh, it's gonna be
We're running out of time. What's the equation?
R squared plus 6/3 equals R plus.
We just talked about on the homework how to square that. You'll get two answers because it's a quadratic. Maybe, maybe not. Actually, in this case, it won't be a quadratic, it'll be linear. Okay. Day 6 for homework tonight.
Finish. I have like the second to last problem.
Finish it. I'll give you a pass the next period.
I want to take
Think about it, it's like, kind of just go off.
See ya.
In his regular.
They show both left hands today.
Oh. But you don't see them, like, you don't want to
Dude, I got, I got 3 skateboards.
You got 3 skateboards? Why?
Yeah, awesome, dude.
Woo!
No, I got 2 tables and
Oh,
How'd you get all of them?